Our problem is from GATE 2021 mathematics paper, question number 48. The problem given is the number of zeros counting with multiplicity of p of z, where the p of z is the polynomial 3z to the power of 5 plus 2i times z square plus 7i times z plus 1 in the annular region, a subset z contained in C such that 1 less than mod z is less than 7 is dash. So it is asked to calculate the number of zeros of this polynomial given p of z inside this annular region 1 less than mod z less than 7. So the NPTEL reference to solve this problem is Module 1 Lecture 2 of the Advanced Complex Analysis Part 1 lectures. The title of this lecture is The Argument Principle, Roche's Theorem and the Fundamental Theorem of Algebra by Dr. T.E. Venkatabalaji. He is from Department of Mathematics, IIT Madras. Even you can watch this lecture using this YouTube link. So now coming to the solution. So it is given the polynomial p of z as 3z to the power of 5 plus 2i times z square plus 7iz plus 1. We solve this problem using the Roche's theorem. So first of all, let me write the polynomial. So given p of z is the polynomial 3z to the power of 5 plus 2i z square plus 7iz plus 1, and the annular region is z in C such that 1 less than mod z is less than 7. That means the annular region is like, suppose this is the circle of radius 7 with center origin. This is mod z equal to 7, and suppose this is the circle of center 0 with radius 1, that is mod z equal to 1. So now the annular region is the shaded region, that is this. So now we have to calculate the number of zeros of this polynomial p of z inside this shaded region. So for this we use the Roche's theorem. By using the Roche's theorem, first of all we calculate the total number of zeros inside the whole circle, big circle with center 0 and radius 7. That is, first of all we calculate the number of zeros of this polynomial p of z inside the circle mod z equal to 7, and then we calculate the number of zeros of the same polynomial inside the circle mod z equal to 1. So then we subtract the number of zeros of this polynomial inside this small circle mod z equal to 1. Then we get the number of zeros of this polynomial inside this shaded region only. That's how we solve this problem. So for this, first of all we calculate the number of zeros of this polynomial p of z inside mod z equal to 7. So firstly we calculate the number of zeros of f of z, sorry, p of z, the given polynomial inside mod z equal to 7 by using Roche's theorem. So for to use Roche's theorem, we have to we have to select two functions f of z and g of z such that mod g of z is less than mod f of z. Then we can say the number of zeros of f of z and f of z plus g of z are same inside mod z equal to 7. So firstly, let me rewrite let me write the Roche's theorem statement. So the Roche's theorem tells us that for analytic function we have for any for analytic functions f of z and g of z on d union dou d with no zeros on the boundary dou d, and if we have g of z is less than modulus of f of z on the boundary dou d, then the number of zeros of f of z and f of z plus g of z are same in d, inside d. So now by using this theorem, we calculate the number of zeros of this polynomial p of z inside the circle mod z equal to 7. But the question here is how to select the functions f of z and g of z. So for this, by using the same given polynomial and the circle mod z equal to 7, we have to select the functions f of z and g of z. So to simply since so our so if we see at the Roche's theorem statement, we can say the number of zeros of f of z and f of z plus g of z are same inside D. So to easily calculate the number of zeros of f of z plus g of z, we should select the function f of z in such a way that we can calculate the number of zeros of f of z inside D easily. For that, and by selection of f of z, we choose the function g of z, and we have to choose the functions f of z and g of z in such a way that this condition also holds. So for this problem, I am choosing the function f of z and g of z in the following way. So I choose the function f of z as 3 times z to the power of 5 and g of z as the remaining part of the polynomial, that is 2i times z square plus 7iz plus 1. So if we choose the functions f of z and g of z in this manner, then on the circle with radius 7, that is on mod z is 7, we have the absolute value of the function f of z as modulus of 3 times z to the power of 5. So that is 3 times mod z to the power of 5. Since we are considering on the circle mod z is 7, so I can replace mod z as 7. So in total we have this as 3 times 7 to the power of 5. That is the absolute value of the function f of z. But whereas the absolute value of the function g of z is the absolute value of the polynomial 2i times z square, this is z, plus 2iz square plus 7iz plus 1. So for this, we calculate the upper bound for this g of z, whereas for the function f of z, since there is only one term, so we can easily calculate the exact absolute value. But whereas for the function g of z, since there are three terms, so we calculate we calculate upper bound on the circle mod z is equal to 7. So by the absolute property, we have the absolute value of the function g of z is less than or equal to modulus of 2iz square plus modulus of 7iz plus modulus of 1. So in total we have this is less than or equal to 2 times mod I times mod z square plus 7 times mod I times mod z plus 1. And since we are calculating on the circle mod z equal to 7, so I can replace the value mod z 7. So in total we have this is less than or equal to 2 times 7 square, since the absolute value of the complex number I is 1, that is modulus of I is 1. So in total we get this as 2 times 7 square plus 7 times 7 plus 1. So now we can see this value is less than 3 times 7 to the power of 5. That is nothing but the absolute value of the function f of z. So in total we have modulus of g of z is less than modulus of f of z on the circle mod z equal to 7. So we can say, so f of z and f of z plus g of z has same number of zeros inside the circle mod z equal to 7. And we can see the number of zeros of the function f of z, since it is 3z to the power of 5, and all the roots of this polynomial 3z to the power of 5 is the origin only, and which is repeated 5 times, that is the multiplicity. So and since f of z equal to 3z to the power of 5 have 5 roots inside mod z equal to 7, the 5 roots are nothing but zeros only, since we have to calculate counted with multiplicities. So we are considering there are 5 zeros of this polynomial. So we have the total polynomial p of z, that is nothing but f of z plus g of z, that is nothing but the whole given polynomial 3z to the power of 5 plus 2iz square plus 7iz plus 1 have 5 zeros inside mod z equal to 7. But the given annular region is, we have to subtract we have to subtract the circle mod z equal to 1 from the circle mod z equal to 7, that is our annular region. So for this we have to calculate the number of zeros of the same polynomial, this the given polynomial inside the circle mod z equal to 1. So for this So now we calculate the number of zeros of P of Z inside the circle mod Z equal to 1. So for this, since in the case mod Z equal to 7, we have chosen the functions f of z and g of z in such a way that the zeros of the function f of z can be calculated easily. So for that, I have chosen the function f of z as 3z to the power of 5 and g of z as the remaining polynomial, and it has to satisfy the condition g of z is less than f of z. One can ask why you choose 3z to the power of 5 only as f of z. One can choose the term 2iz square. In this case also we can calculate the number of zeros of this term 2iz square easily, but when we choose 2iz square as f of z, then the condition g of z is less than absolute value of g of z is less than modulus of f of z may not hold on this circle, since we are considering the circle as mod z equal to 7. So what to choose the functions f of z and g of z depends on the circle also. So to calculate or to choose the functions f of z and g of z appropriately, one can try the trial and error method also. By choosing f of z as 3z to the power of 5, one can choose this way, or one can choose 2iz square as the another case, and one can check whether this condition holds or not. Or one can next select 3iz as f of z and can check whether this condition holds or not. By trial and error method, one can select the function f of z correctly. So for this circle mod z equal to 7, I am choosing 3z to the power of 5 as f of z. But coming to the case mod z equal to 1, the question again here is what to choose f of z. Or let me write another functions, since we have already chosen f of z and g of z. So write, let me choose, or let me write the other notations. So we choose r of, I'm considering in this case mod z equal to 1, the functions as r of z and s of z. So the question here is how to choose the function r of z and s of z. So for this, since it is the given polynomial and it has to satisfy the condition r of z is less than s of z on the circle mod z equal to 1. So for this, I am choosing s of z as 7iz, and the function, or let me take this as r of z 7iz, and the remaining part of the polynomial f p of z, that is 3z to the power of 5 plus 2iz square plus 1 as s of z. Then on the circle mod z equal to 1, we have the absolute value of the function r of z, that is as we have chosen modulus of 7iz. So by the property of absolute value, absolute function, so we can rewrite this as 7 times mod I times mod z. But since we are considering the circle mod z equal to 1, so I can rewrite mod z as 1. So this is nothing but 7 times 1, that is equal to 7. But whereas coming to the absolute value of the function s of z, that is the absolute value of the polynomial 3z to the power of 5 plus 2iz square plus 1, and this is less than or equal to modulus of 3 times modulus of z to the power of 5, or mod z to the power of 5 plus 2 times mod I times mod z to the power of 2 plus 1. And since our circle is mod z equal to 1, so I'm just replacing mod z with 1. So in total we get this as 3 times 1 plus 2 times 1 plus 1. So that is equal to 6, and which is less than 7. That is nothing but the absolute value of the function r of z. So in total we have modulus of s of z is less than modulus of r of z on the circle mod z equal to 1. So now again by Roche's theorem. So by Roche's theorem we have, or we get, the number of zeros of r of z and r of z plus s of z are same inside the circle mod z equal to 1. Since in this case mod z equal to 1, we have r of z is greater than s of z. So and since r of z, that is by the choice of, by our choice 7I z, has only one zero inside mod z equal to 1. So in total, therefore r of z plus s of z, that is nothing but the whole polynomial, which is nothing but the p of z. This is chosen in such a way. So the p of z is nothing but 3z to the power of 5 plus 2iz square plus 7iz plus 1 has 1 0 inside mod z equal to 1. In this case also, one can have some doubt that why we should choose r of z and s of z in this way only. We are choosing the functions r of z and s of z in this way, so that the condition r of z, sorry, s of z is less than r of z on the circle mod z equal to 1. Or one can check the choice of r of z by trial and error method. That is, instead of 7iz, one can choose 2iz square and can check whether s of z is greater than r of z. Or one can check by taking 3z to the power of 5 also, whether in that cases are we getting s of z is less than r of z. By that trial and error method, we can see the only case, as r of z has this function and s of z has this function. When we choose in such a manner, then only we get s of z is less than r of z on this circle mod z equal to 1. So by choosing in this way, we got the function or the polynomial p of z as the given polynomial has 1 0 inside mod z equal to 1. But the question in the problem, it is asked the number of zeros inside the annular region as this. So as we have already calculated the number of zeros inside the circle, mod z equal to 7 as 5, and we have calculated the number of zeros inside this smaller region mod z equal to 1 as 1. So when we subtract, that means what does this means is, so there exist 5 Or firstly, let me write there exists one zero inside this smaller circle, and whereas the, there are four zeros somewhere inside this bigger region mod z equal to 7. So in total, we have, as it is asked to calculate the number of zeros inside this shaded region only. So there are four zeros, which is not inside this smaller circle mod z equal to 1. So in total, we have, so 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 the number of zeros of p of z inside the annular region, as z belongs to C, such that 1 less than mod z is less than 7, is the number of zeros of p of z inside the circle mod z equal to 7 minus the number of zeros of p of z inside the circle mod z equal to 1, and that is nothing but 5 minus 1, so that is equal to 4. Hence the total number of zeros of the polynomial p of z inside this annular region is 4. Hence the answer is 4. Thank you.